Hello and welcome to today's lecture. Today we are going to review the basics of photovoltaics. For the purpose of this lecture, I'm going to reuse some of the slides that were part of the lecture last year. So for that, I have to thank Dennis Prozan, and Steve Blair and Mike Scarpilla. They're both professors here at the University of Utah, and they have some interesting research going on in the field of photovoltaics. If any of you is interested in looking that up, okay. Just to begin with, here's the outline of what we are going to go over today. Firstly, I'm going to talk about what we mean when we say the term photovoltaics, what it encompasses, what photovoltaics is mostly used for. Then we are going to look at why do we want to use photovoltaics in the first place, and which leads us to the obvious question of what is the current state of photovoltaics around the world. Thirdly, we are going to look at how solar cells work, which comprises the largest part of photovoltaics, and how do we measure the quality and efficiency of solar cells. So a part of this third section, the measurement of photovoltaics um, was discussed in the last lecture. So I'm going to go over that briefly because I'm sure most of you are by now familiar with these kind of measurements of photovoltaics. And lastly, we are going to discuss what type of solar cells are out there and what kind of engineering has gone into making the state-of-the-art devices. Just let me make sure I am recording. Yeah. Okay. Okay, so a little background on solar cells. We can trace the um, first piece of science which is involved in photovoltaics, namely the photovoltaic effect, as far back as 1839, and Henry Becquerel is credited with inventing the inventing the science behind the photovoltaic effect. Turns out that he was only 19 years of age when he came up with the idea of photovoltaic effect. Following that, a lot of progress was made by Braun in inventing the rectifying metals and lead sulfide contacts, which go into these kind of devices around the end of the 1800s, 1870s. Then you're familiar with the name of Walter Schottky and Neville Mott, who are created with coming up with the theory of metal semiconductor diodes, as you will see, without which the overall science of solar cells would not be possible. And finally, Russell Lowell and Jack Schaff are credited with discovering the engineering of doping effects in silicon and germanium to create what is called pn-junctions around the 1930s, the early 1900s, at Bell Labs, which is now AT&T Labs. And if you want to look more into the history behind photovoltaics, you can check out this link over here. So, in as far as a general term is concerned, what are photovoltaics? So, very simply put, if I am to look at this as a black box problem, the problem is that we have all this energy which is incident on the earth from the sun, which is the solar irradiance from the sun, and we want a way by which we can convert that solar energy to electric current. And let's assume for a moment that that black box is what solves this problem. And as we will see later on, that this black box is basically the photovoltaic um, components, namely solar panels, solar cells, and so on. So the problem that we are trying to solve using photovoltaics is how to take all this energy which is incident on the earth from the sun, the solar irradiance, and convert that into electric current. Once we are done with that, the larger part of the problem is solved. Then we can have some control devices, which are basically electrical components, such as charge controllers, battery systems if we want to use DC power, and our inverters if we want to convert this generated power into AC power for distribution across power grids and so on. So To summarize, the direct converters of light into electricity is what photovoltaics is used for. A photovoltaic cell can be thought of as a backward LED. What this means is in an LED, you use electric current to produce light. In the case of photovoltaics, you're basically doing the opposite. You're using light to produce electric current. So it works like a backward LED. And it's a giant semiconductor diode. And we'll see more in detail as we go forward with this lecture, what this means and how this goes into the science of photovoltaics. So the question is, why do we need to think about this problem in the first place? I mean, we have been using conventional electric generators for such a long time. And if we do a little bit of math in this, we can see that the efficiency of solar cells is much greater compared to that of conventional electric current generators. Um, First, we have to think that, okay, where do we get our electric current from? It's basically from steam turbines and generators, which are run using combustion. And what is the fuel in this combustion? Basically coal. Coal is burned to generate steam, which runs steam turbines and generators. And where do coals come from? Coal comes from the long uh, uh, plants and animals which were alive on this earth millions of years ago, and then after they died, they were compressed under tons and tons of earth, soil, and rock, and that heavy temperature and pressure caused the decomposed plants and animals to basically be converted into some sort of either coal or petroleum fuel and so on. Basically, plants are usually converted into coal, which we later uh, use for combustion to generate electricity. And ultimately, where do plants get their energy to live from? Sunlight. So if we do a bit of efficiency calculation, the amount of sunlight that plants can convert to energy to live off of is basically 3 to 6%, which comes from photosynthesis. After the plants die and they turn into coal, a process which is millions of years long, um, we modern humans go and mine this coal and use it for combustion, which is about 50% efficient. Steam turbines and generators are much better, operating at 95% efficiency. But if you combine these efficiencies together, you will get a net efficiency of 0.5% starting out from the sunlight to the final electric current generation. Now, if we are to look at photovoltaics, what we can see that if you remember this black box problem, solar cells or solar panels which can convert the solar irradiance directly to electric current, we can see that solar panels are about 18% efficient. This is quite a conservative approximation because the state of the art or research and development solar cells have actually been shown to provide greater efficiencies, around 30% and so on, even larger efficiencies. But let's take a conservative approximate efficiency value of say 18%. And then we have our control electronics, which are shown over here, the charge controllers, battery systems, inverters, and so on, which are, again, about DC AC inverters, about 95% efficient. So what we get is a net efficiency of 17%. So it definitely makes sense, just from an energy efficiency point of view, to invest in photovoltaics and make them the more adoptable technology for generating electrical energy. And where can they be used? They can be used in many different places. I'm sure you guys are familiar with this picture. It's been used in lectures before as well. You can use solar concentration arrays. You can use photovoltaic solar cell panels on roofs. And you can also even have them on stuff like aircrafts and cars, which look like from another planet. You can use them on satellites, power small electronics like speedometers and calculators, and sorry, um, and even parking meters and so on. So they can be basically used anywhere to power any kind of electrical devices. The current world's largest utility-scale solar power generators, photovoltaic generators, um, There's one at the Tengger Desert Solar Park in China, which can produce up to 1500 megawatts of electrical current, which is enough to power about 200,000 households. There's also another power station again in China which can produce 1000 megawatts with for its phase 1 production, with a projection of up to 3000 megawatts when it expands to phase 3. So definitely China is doing very well when it comes to adopting solar power for electrical power generation. Here is the current state of photovoltaics, and I got this chart off from the Renewable Energy Policy Network report for the year 2016, and it shows that obviously this has progressed much better over the last couple of years. But if we are just to look at how the state of the photovoltaics progressed from 2005 to 2015 over one decade, we can see that we have been able to produce up to 4.8 gigawatts per year as a world total, which is up from less than 1 gigawatt, about less than half gigawatt. So definitely there's a lot of progress going on over here. And one interesting thing to see is that Spain is doing very well. They're leading the charge when it comes to solar photovoltaics power generation. That's very promising. This is also interesting. If we don't want to think of, okay, the environmental factors and energy generation and so on, we can still see that the number of jobs in renewable energy is increasing, and this increase is largely due to the fact that jobs in solar energy, which is shown over here, has increased a lot. There's about a total of 8.1 million jobs. If some of you are interested in doing something exciting, fun, and also something which is good for the environment and good jobs, this is definitely one place to look. Okay. So now at this point, let's think about what is the potential of photovoltaics. And we can get an idea if we look at this quite simple problem. So it says over here that the solar flux is about 90,000 terawatts. So that's the total solar flux, the total irradiance from the sun which is incident on the earth. It's about 90,000 terawatts. Now the global primary energy consumption, that's the total amount of energy which is consumed by the entire population of the earth in 1 year, is about 20 terawatts. To be more precise, it was about 16.9 terawatts in 2013. The current global primary energy consumption is about 20 terawatts. So here's the question. So let's say we assume a 17% power conversion efficiency, which is at par with the average efficiency of solar cells, as we saw over here, that solar panels are about 18% efficient, being conservative of numbers. So at 17% power conversion efficiency, if we are able to extract only about 0.13% of the sunlight which is hitting the earth, say 0.13% of 90,000 times 17% of that, we would be able to fulfill the entire global primary energy consumption of 20 terawatts. And you can work out the math. So you see these are very, very conservative numbers. It's less than 1%. It's much less than 1%. It's just 0.13% of the sunlight which is hitting the earth, with a 17% power conversion efficiency of that figure, is more than enough to produce the entire global primary energy consumption of 20 terawatts. And lastly, since these are numbers, it would be good to get a feel of what this means in real life. So the question is, how many solar panels do we need to produce that? And which translates to how many square miles of solar panels would we need to install in order to be able to get this solution to this problem. This is a very interesting solution, and it turns out that the number of square miles is approximately equal to the area of the state of Texas. And that would be enough to power the entire globe for a year. So if we were to cover the entire state of Texas in solar panels and generate photovoltaic power from just that region, that would be more than enough to sufficiently generate all the global power consumption required in 1 year. Of course, this means that no one's going to really do this, but we can distribute this number of solar panels across the globe, across different states of the United States and across different countries. And what this shows is it's not a lot. Sometimes people think that, okay, the efficiency is 18%, so that must mean that we need hundreds and thousands of, yes, you need hundreds and thousands, but compared to the entire area that is available to us for production of photovoltaics around the world, it's very conservative numbers. It's nothing which is not doable or which is impossible at this point of time. But what really comes down to why the solar power or why photovoltaics is not popular is, the way I understand it, is because of the percent cost of generating electricity. At this point, as we will see in the next couple of slides, conventional electric current is still cheaper percent when compared to photovoltaics, and really the end consumer is not going to really think in the long term in terms of environment and so on. So if you are to make a technology popular in the amongst the masses, you have to make it cheaper compared to the conventional technology which is out there in the market. At this point of time, when if someone is interested in installing photovoltaic solar panels and so on in their homes, they really have to think that, okay, I have to put in some investment for at least for the next 5-6 years, after which I will be able to start making some profit, or I'll be able to start generating cheap electrical power or living off the grid, if you may. But most of the people are not interested in, say, 5-6 year investment plans. So if we are able to reduce the present cost of photovoltaics to be less than what is the current cost of conventional electric current, then we should be able to convince more people to adopt this technology, which in the long run is very good for our environment and so on. So here is an interesting website. This is from the National Renewable Energy Lab, and what this shows us is the map of the United States. And if you click on each of these states, you can get different data like solar irradiance and so on. So I can show you, like over here, if we go to the National Renewable Energy Lab website, it's the link which is provided over here. You will see this map, and this is an interactive map, and you can click any of these states to get information on the solar irradiance and how much photovoltaic power can be generated and so on. They have very useful maps over here for global horizontal solar irradiance over different time periods. Photovoltaic power generation. Suppose if I were to go up and click on Utah, it shows me the total solar irradiance of our state. And as you can see, and this might be helpful for some of your projects, if any of you are going to work on photovoltaics, then you can definitely make use of these maps and get useful data, because this is real-time recorded data by the Renewable Energy Lab. So you can definitely use these kind of data and make your projects very presentable. And what we can see is, if you look at this map over here, the distribution of the solar irradiance is definitely non-uniform, because the fact that the Earth is a globe. So regions which are closer to the equator will definitely get more solar irradiance if you are to average it over the course of a year. And as you move further north or further south, then you would definitely have less solar irradiance. So definitely it makes sense to have most of solar panels or most photovoltaic power generators distributed across countries or states which are closer to the equator. Okay, so next we come to the DOE Sunshot initiative, which was launched by the Department of Energy in 2011 with a goal to reduce the total cost of solar energy by a sufficient amount so that it would be adoptable by the larger mass of the population. This is what I was referring to as a goal to reduce the cost of solar power to be less than what the conventional cost of generating electric current is, so that it is cheap enough to convince the global mass to adopt this technology compared to conventional electric power generation. So as we can see the Sunshot progress and goals chart, sorry. So here we can see basically they have three types of markets that they want to address. First is the residential, then commercial, and then utility. And you can see in 2010, the cost of solar power was about 52 cents. Now we want to reduce this so that it's cheaper than conventional electric current generation. So it says this cost reduction corresponds to utility scale solar costing approximately $1 per watt or 6 cents per kilowatt hour, making solar power or solar energy a possibility for millions of people in US. And you can do this similar kind of analysis for different countries across the globe. And we see that the target of 2030 is to be less than 6 cents, about 5 cents, 4 cents, 3 cents. And right now we are doing very good actually. From 2010, over the course of the last 7 years, the total cost of power in cents per kilowatt hours has reduced from 52 to 16, and it's projected to go up to 10. And finally we hope that we will be able to meet the 5 cent mark. And if you guys have some good ideas on how to generate cheap photovoltaic power, sorry, photoelectric power is something different completely. So photovoltaic power, solar powers, you are more than welcome to contribute to the DOE Sunshot initiative. You can look up the name online, and you can see how you can contribute to this kind of technology. Okay, so before I go over to the materials and the more technical part of solar cells, I would like to pause here to see if you guys have any questions. Okay, so the second part of the solar cells lecture, we are going to look into what materials make solar cells. So first, this graph over here on the top left shows us the spectral irradiance versus wavelength. So what we see, and I'm sure you guys are familiar with this from the last class. So this black curve shows the ideal black body spectrum, a black body radiation spectrum of 5000 degrees Celsius. Now this yellow curve, this yellow distribution is for sunlight at the top of the atmosphere, and the red distribution is for the sunlight radiation at sea level. What happens, you can see, is that once the photons from the sun have to pass through the atmosphere, due to the presence of different gases like mostly oxygen, water, carbon dioxide, and so on, a lot of them are absorbed. So you get these dips over here which are shown, and the corresponding gases which are responsible for these absorptions are also shown over here, like oxygen, water, carbon dioxide, and so on. So we start out with this yellow band at the top of the atmosphere, and then we are left with this red band of the solar radiation at sea level that we have to work with. And we have to make sure that we can improve the efficiency of the photovoltaic technology sufficiently so that we can make the best of absorption and conversion of those absorbed photons to electric current based off this red graph. Now secondly, how do we absorb these photons? Now the idea comes from the fact of the energy or the energy band gap, which is present in metals, semiconductors, and insulators. If we look at metals, the conduction band and the valence band overlap, and there is no energy gap. If we look at insulators, there is a large energy gap, and in semiconductors, it's in between these two. Now, if we have a material with a band gap which is equal to the energy of a photon, then it can absorb that photon and cause a state transition of electrons from the valence band to the conduction band, thereby giving rise to electric current. Now we can do a graph, we can plot a graph of efficiency versus band gaps, and we can see that there are different materials which are identified, across that band, because no one material has a sufficiently large enough band gap to absorb across the spectrum of solar irradiance from UV to IR. So we have different materials which are very good and which have good efficiency at absorbing at different band gap values. But as you can see, the efficiency is about 0.25% to 0.3% maximum. Okay, so now next we look at how a solar cell works. So this is basically a cross section of a solar cell. What we have, the most important part is the absorber layer, which is responsible for absorbing the incoming photons and generating the potential difference, which is responsible for generating electric current when a load is connected across the solar cell. We have back contacts and we have top contacts or front contacts. There's transparent conducting oxides and pn-junction partners, which are responsible for the for carrying the charge across the device. And lastly, we have glass, which acts like a backing for the solar cell. Now, if we are to connect a load across the front and back contacts, we can power the load using the electricity which is produced by the solar cell in presence of photons. Now, the three necessary functions which this device does is first to generate charge carriers from semiconductors and sunlight, separate these charge carriers using a pn-junction diode process, and finally collect the charge carriers to do electric work, which is basically to power this load. So here we see the science behind the creation and charge separation in PN junctions. Actually, we can look at this video which describes this in good detail. So here we see the PN junction solar cell uses a semiconductor such as silicon. Now it says the atomic scale structure of silicon is shown here, which is good. It's shown in 3D. In this case, I had this diagram drawn in 2D. You can see the silicon atoms and so on with their corresponding electrons. And then it says that impurity atoms can be added to the semiconductor to increase its conductivity by a process called doping. So here you can see this red atom is an impurity which has been introduced into the silicon. And we see that over here, the red is a boron impurity and the green is a phosphorus impurity. Now, based on what kind of impurities these are, we get different effects in the doped silicon. You can see boron has one less electron compared to silicon atoms. So when boron is doped into a silicon lattice, we have a missing electron. Silicon has 4 valence electrons, boron has 3. Phosphorus, on the other hand, has 5. So when phosphorus is introduced as a doping element, we have 1 extra electron, which is shown over here. Negative charges called electrons are introduced by doping with atoms containing more electrons than silicon. Like I said, with phosphorus being extra, these electrons are not tied in the chemical bonds and are free to move about. In the case of boron, what we see is since there is an absence of an electron, this can be thought of as the presence of a positive charge called a hole. So just like an electron in this case is allowed to freely move about the lattice, a hole can be also thought about freely moving about the lattice. And this doping concentration has to be very low. It needs to only be millions, 1 in millions, with respect to the concentration of the silicon atoms. So these two types of doping gives rise to two types of semiconductors. One is the N-type semiconductor and one is the P-type semiconductor. In the N-type semiconductor, we have free electrons, and in the P-type semiconductor, we have freely moving positive charges or freely moving absence locations of electrons or holes. So when these two types of semiconductors are joined together, they form what is known as a PN junction. So P-type semiconductor, N-type semiconductor, and this is the PN junction. The electrons can wander across the junction, or the holes can also do the same thing, leaving behind one location which is free from an electron, or basically a positive charge. When the electron goes to the other side, it combines with the hole and disappears. The same can happen when a hole comes onto the N side, leaving a negative charge on the p side and is then recombined with an electron on the n side. This can continue happening, and what we are left with is a region of depleted charges across the junction, and this region is called a depletion zone. You see, the separate static positive and negative charges mean that there is an electric field across the depletion zone, which is determined by the positive charges on the n side and negative charges on the p-type semiconductor. Now, when energy from light is absorbed by the semiconductor, it's going to dislodge an electron, creating an extra mobile charge, as we see over here. So the electric field now makes the electron flow to the n-type material and the hole flow to the p-type material. And thereby, we get the effect of photo generation of charge carriers, which is basically the photovoltaic effect. The resulting separation of positive and negative charges across the junction is called a potential difference or voltage, and since this voltage is generated by photons, it's called photovoltaic effect. Now, if you connect any load across this PN junction solar cell, you can basically power the load using the charges which are driven around the circuit in the form of an electric current. Okay, so that's basically, and this is basically what the video showed. I think that was more useful. Now, since now we know how, say, the solar cell works and so on, but suppose we have to analyze the electrical circuit of a solar cell, we have to understand how we can distribute all the different components which go into the working of a solar cell into electrical components that we can then analyze in the form of a circuit. Now, we saw over here that the solar cell is a combination of two effects. One is a diode type effect, which is basically comes from the PN junction diode, and the second is a photocurrent source, basically the generation of electric current from photons. So when we have to write the equivalent circuit of a solar cell, we write it like this. It's a combination of a photocurrent source. You see, this is a current source, IL, a photocurrent source, and a diode. These two we saw from the video, the diode type behavior, which is caused by the PN junction diode formation, and the generation of electric current from photons, basically a photocurrent source. Now, due to the presence of, I'll actually skip to this slide. It shows the photocurrent source and the diode. Now, due to the presence of defects in the solar cell, we have two types of resistances. One is called the shunt resistance, which is shown over here. The shunt resistance is caused by defects in the formation of the solar cells, the PN junction, and the other one is a series resistance. The series resistance comes from these contacts over on this side and over on this side. The resistance which is introduced into this device by means of these contacts is called the series resistance. So the entire solar cell can actually be described using these four components. So these four together is the solar cell. You have a photocurrent source, you have a diode, you have a shunt resistance, and a series resistance. The shunt resistance, you can see, is in parallel with the circuit, and the series resistance is in series with the circuit. Now, if we connect an external load across these two terminals, we can power the external load using the electric current generated within the circuit. So it is very important to remember that we can break up a solar cell into these four different components, and now we can analyze each of these components separately to see how they affect the overall performance of the solar cell. So first, let's look at the current voltage curve, which we typically have for all electrical circuits to help us analyze the performance of the device. And we see that because the solar cell behaves and is actually made up of a PN junction diode in reverse bias, the current voltage curve of a solar cell follows the exact same behavior of reverse biased PN junction diode, as is shown over here. It's basically when there is no photons or there is no light incident on the solar cell, the current voltage behavior of the device is shown with this black curve. Now, when there is photocurrent incident on the device, you get generation of electric current, which is shown over here. Of course, you can always flip this curve to get positive values. It's just based on convention. But this difference in the current which is produced is called the short circuit current. And basically, the trend of the curve remains the same, except that the curve is then shifted down, and it's the same curve with the added photocurrent which is generated. So the idea is that the final curve, or the light, meaning when photons are incident, the light current voltage curve is basically the dark current voltage curve shifted down by the generated light current without changing its shape. So it's very easy to now understand what is going on, because you have the diode part and the photocurrent source. So the diode part is responsible for the trend of the black curve, and the photocurrent source is basically shifting the curve downward by the added photocurrent. If we are now to plot the power versus voltage, power being equal to the current times the voltage, we get a maximum power which is shown over here for the voltage versus power performance of the device. And so yeah, and of course the maximum power is equal to the product of the maximum current and the maximum voltage. That's obvious. And now let us look at how the shunt and the series resistances affect the performance of this device. So the shunt resistance, because is a resistance which is connected in parallel, is going to have an effect which is, so this equation shows the current versus voltage equation for a diode. Let's see. For a diode over here, and what we see is that we have to then add the photocurrent which is generated by the incident photons. And since the shunt resistance is connected in parallel, we have to subtract the current, and the current is given by the voltage over the shunt resistance value. So we see that the larger the value of the shunt resistance is, the smaller this term becomes, and the greater the term of the current becomes. So it means that the larger the value of the shunt resistance, the better the performance of the solar cell. So here is a very good an applet that I found from this website called pveducation.org. It shows you the effect of the shunt resistance, and it's basically, this is the figure that I had in the slide. And if you then come down over here, if you make the shunt resistance as big as possible, so this is 10 raised to 4 ohm centimeter square, you see the curve, the solar cell with the shunt resistance matches very well with the ideal solar cell curve. Now basically this curve is just the flipped version of this curve over here. You can see they just flip the convention. And if I decrease the shunt resistance, you can now see that the curve becomes much poor, and you lose efficiency in the solar cell. So this is very helpful, and you can use this later on to, if you're working on any projects related to photovoltaics, you can definitely analyze your device using these kind of curves. Then secondly, the series resistance, because the series resistance is connected in series, the series resistance has to then, obviously it becomes very obvious that the series resistance has to be low for better performance. So if we now just look at the series resistance and its effect, we can see the lowest series resistance gives us the best performance and the best power. If I then increase the series resistance, the power goes down and the performance of the device, or the current generated, goes down as well. So you can definitely look at these web pages. It's given over here, and it's very useful. This slide shows basically what I just described, that a shunt resistance, when it becomes a large value, like from 10 to 10 raised to 6, the curve becomes better. And the series resistance, when it decreases, say from 20 to 0, you get a better looking curve. That's all. I think the These applets are more helpful. Okay. And lastly, what other kind of losses do we have? We have quantum efficiency losses due to recombination effects. This is something that we discussed in the last lecture in the measurement of photovoltaics. The most ideal quantum efficiency curve is basically this box from from 0 to 1. This box over here is the ideal quantum efficiency curve. And obviously, that's not possible because all different wavelengths of light are not absorbed in the same manner, or they have different types of effects when it comes to material photon interactions. There is a reduction in the blue band due to front surface recombination, and there's a reduction in the red response due to um, rear surface recombinations and absorption of long wavelengths. And there is also a reduction in the overall quantum efficiency caused by reflections and low diffusion length and so on. So we never get a box curve like this, the ideal box curve, we get something like this. So these are also losses that we have to take into account when designing devices. Okay, so the third part of the lecture is going to deal with, actually this is the last part of the fourth part of the lecture, sorry, is going to deal with different kinds of solar cell technologies, generations that have existed and the current state of the art, and some research type solar cell designs. So before I start that, if you guys have any questions, I'm going to pause for a moment here. Okay, so last part, the solar cell technologies. There's been three identifiable generations of solar cell technologies. The first generation is where we had monocrystalline or polycrystalline bulk silicon solar cells. In the second generation, we had thin film solar cell technologies, organic photovoltaics, and organic organohalides. So basically, a combination of organic and inorganic technologies called perovskites. In the third generation, we have multi-junction technologies and other different advancing research technologies for photovoltaics. So we see that this is a distribution at 2010 of different solar cell productions by technologies. The largest part is the first generation, the standard crystalline solar cells, and then there is a fairly large contribution with respect to the others of thin film solar cell technologies. Cadmium telluride, which we will see in a couple of slides later, is doing good, and then we have other different technologies. So first generation monocrystalline polycrystalline solar cells, um, crystalline silicon solar cells. So here is the conventional solar cell technology. This is from Dr. Charles Gay at SunPower Corporations, and we see the cross section of a typical solar panel. What we see is in the bulk we have the pn-junction, and then on top and bottom we have anti-reflection coatings and different textures to increase the light trapping potential of solar cells, aluminum plates on the backs, and the grid lines for the front and back to connect the top and back contacts. Now these kind of solar cells are only about 15% efficient, and the losses primarily come from these sources. There's reflection losses from the metal grid lines. There's reflection losses from the top surface, which is much lower compared to the reflection from metals. There's heat losses, which is the I square R, so current squared times resistance. So heat losses contribute about 0.5%. There's recombination losses inside the material, and then there's losses from the back surfaces as well. So if losses were to be ignored, this kind of a device could perform at about 30% efficiency. But due to about 14.3% losses, we get a final efficiency of about 14.7% of these kind of devices. So here is also an interesting technology. You see this textured top surface. Well, this is kind of a problem that you guys could think about. Is if I have a material, suppose this is the pn-junction material, and I have light incident on it. So what would happen is, if you remember one of the problems from the midterms, a light is incident on this slab and it refracts into the device and then refracts out. How can I think of a way to solve this problem of making the light or the light photons remain trapped within this device or within this slab much longer? The first thing we can do is simply not allow it to go out of this device by putting a reflective layer on the backside. So if that is the case, then the photons would reflect off this reflective layer and at least firstly have twice the time that they remain inside the slab. So from here to here and then back up here. Then they can escape from the front surface. Now obviously we can place another reflective layer, then we would not be able to have incident photons entering the slab in the first place. So what we do is we make this surface textured so that when the light tries to go out, it sees some kind of angles which present the case of total internal reflections. And if we optimize this texturing, we can have light reflecting back in and being inside the slab much longer. We can also texturize the back surface to keep increasing this effect. And these kind of structures or designs can be optimized using different kinds of optimization algorithms. So this is something that SunPower was able to do, and they also solved problems of these contacts to come up with this kind of a device. Where firstly what they did was they removed all the contacts from the top surface and they made them into all bottom contacts. Secondly, they made the top surface only textured and no metal grid lines, thereby reducing the losses due to metal grid lines and so on. And by this method, they were able to increase the efficiency of their solar cells to 25%. So from 14.75% to 25%, that's a big jump. And this is a good example of how you can use different clever tricks and how you can solve these kind of problems. And this is definitely what you guys should look at when you're doing something interesting for your projects, like how to solve these problems. So you see how systematically they went about solving this problem, and thereby that led to an increase in the overall efficiency of the solar cell. This is a 2D cross section of this diagram, which shows all the improvements that they did, and thereby they were able to improve the efficiency of the solar cells. Okay, so second generation solar cells. Firstly, we come to thin film technologies. So thin film technologies, one of the main advantages of using thin film semiconductors is that you are able to exploit the case of direct band gaps. So what is direct band gap and what is indirect band gap? Now, when you have the highest point of the valence band line up with the lowest point of the conduction band, you have the direct band gap. But if these 2 points are not lined up, you have an indirect band gap. A direct band gap increases efficiency because you can have photons which have energies which are perfectly matched with this direct band gap, leading to full absorption of these photons and the excitation of an electron from the valence band to the conduction band. But if you have indirect band gaps, this type of transition is not possible, and so there is a reduction in the efficiency. Now, why thin films of the same material have direct band gaps over bulk materials is a completely different question, and for that is actually reserved for classes which are lectures which deal courses which deal completely with photovoltaics. You can look that up if you're interested in that, but in the interest of time I'm going to skip this. Just know for the time being the thin films, which are about 1 to 4 microns compared to bulk, which is about 200 to 300 microns, can exploit the case of direct band gaps over indirect band gaps. And the best technology that to come out from thin film, and obviously there's other advantages, like for thin films you have a big reduction in weight. One of the important factors that goes into designing solar panels is the power generated per area or power generated per weight, like how many watts per kgs is the device. So if you have a thin lightweight device which can generate the same amount of power as a very thick heavy device, it's always advantageous. So cadmium telluride has made a big progress in this field and is considered the biggest competition to solar cell technology, which uses silicon. We have these two solar farms. One is the Topaz solar farm, which can produce up to 550 megawatts. 9 million solar cells which use the cadmium telluride technology, solar panels. We have the Agua Caliente. Both of these are in, I think the Topaz solar farm is actually in California and the Agua Caliente is in Arizona. Produces 290 megawatts of power from this solar panel distribution. And both of these use thin film solar panels, photovoltaics, using the cadmium telluride material. Okay, next we have organic photovoltaics. So organic photovoltaics is still in the realm of research, and they use organic electronics, basically molecular electronic materials, molecular semiconductors as shown over here. Again, this is a completely different, this is material that can be covered in a completely different course. So for the time being, we can just, we can do a cursive analysis of this technology, whereby we can see the difference between inorganic and organic semiconductors. In inorganic semiconductors, you have clearly defined valence band and conduction band, and the transition of electrons between these bands gives rise to to electric current. And in the case of organic semiconductors, you don't have clearly defined conduction and valence bands, but you have unoccupied and occupied molecular orbitals, as shown over here. So in inorganic case, the absorption of a photon leads to the transition of a free electron from the valence band to the conduction band, thereby generating electric current. But in the case of organic semiconductors, you have highest unoccupied molecular orbitals and lowest occupied molecular orbitals. And when a photon is absorbed, what we get is a creation of an exciton pair, which is responsible for electric current generation. This type of technology can also be used to generate solar electricity, solar power. And lastly, we can combine these two technologies to get organometallic halide devices, which are called perovskites. So perovskites use inorganic and organic, a combination of inorganic and organic materials. So over here you can see a methyl ammonium lead triiodide perovskite. So the organic part comes from the methyl ammonium, which is shown over here, this lattice with the blue dots, and the inorganic part, that's the organic part, and the inorganic part comes from the from the iodide ions and the lead ions, which are distributed inside the lattice in this manner. Now, this kind of structures are also very convenient for generating photovoltaic power. And what we can see is that actually the power conversion efficiency of perovskites have increased from about 4% in 2009 to about 20% in 2016. And this is actually the fastest growing solar cell technology which is present in the market right now. So definitely a lot of incentives to do research in perovskites as far as photovoltaic technology, the photovoltaic generation, power generation is concerned. There's also lightweight foil substrates like polyethylene, polyester foils, and very high power. They have very high power to weight ratio. This is what I was talking about in the previous slide, like how you can make lightweight technology so that you can put them on aircrafts and so on. The lightest or the highest power to weight ratio comes from ultra thin perovskites, which is shown over here. And lastly, the third generation of research and development photovoltaic technology, multi-junction solar cells. You guys have already covered this, and we have discussed this in previous classes. So I'm just, I don't think there's any much need to go over this in much detail. But basically the idea is, instead of using one material with one band gap to absorb across the entire solar spectrum, you will use different materials with different band gaps that can absorb at different locations in the spectrum, stack them up, and thereby increase the efficiency of the overall device. So one junction can get up to 37% efficient, but if you increase the number of band gap, or increase the number of junction solar cells to 2 to 3, so on, you can get up to 50 to 60% efficient cells. So this was also discussed in the last class, quantum efficiency for multi-junction cells. As we can see, different materials absorb at different locations of the solar energy spectrum. Here is also, you've seen this in the previous class as well. Multi-junction solar cells basically are different materials which are located on top of the other and basically stacked, and the different photons with different wavelengths and energies are absorbed by each of these materials separately, and thereby it leads to an increase in the total efficiency of the device. Lastly, we come to an umbrella term for other advancing engineering. One of the technologies we discussed in the last class was solar spectrum splitting, which leads to an increase in the efficiency of solar cells by splitting the solar spectrum and making 2 or 3 devices, 2 or 3 band gap solar cells absorb at different locations. And here is an interesting research which is being conducted using radial junction solar cells. Instead of having a slab of a PN junction, what they have is basically thin rods or wire arrays which are PN junctions inside. So these are radial PN junction wires. And the advantage in this case is you have an increase in the surface area of absorption of the sunlight, and also after absorption, if there's any reflection or radiation, it basically can be again absorbed by any other wire. So you have a large increase in the efficiency of devices using this technology. If you guys are interested, you can check out this interesting paper which is linked over here, which discusses these kind of technologies. So in summary, photovoltaics have grown exponentially over 20 years. Solar cells require absorption, separation, and collection. So we can address each of these problems and try to improve the solutions for these problems to get an overall improvement of the technology. There are a lot of viable technologies, and we have to explore different kinds of materials and find out which is the best answer for the problem that we are trying to solve. And very good efficiency, very high efficiency requires clever problem solving. And we have now entered the 3rd generation of photovoltaics, and we have to think about how we can solve problems in a more efficient manner and make this technology more widely adopted. All right, that brings me to the end of this lecture. And if you have any questions, you can please feel free to ask them. Otherwise,